So it's 25 people now. I don't know how many there will be in the end, but I don't want Amy to wait long for us. So I think I'm going to start the webinar now, hoping and welcoming in more people during my presentation at least. So today I'm very, very pleased to open this first series of webinar dedicating to the Arctic CI, so the Arctic climate in general. This is a specific initiative that includes 4 talks. We have one every week in September. The list of the different talk has been circulating already from the communication division. And it's absolutely a pleasure to start today with Amy Solomon. She's really an expert on the Arctic climate and the interaction in this region between the atmosphere, the sea ice, and the ocean. So today we will start sharing and discuss knowledge and advances in sea ice predictability and sea ice forecasting, mainly in this case. Again, all focus on the Arctic region. Hemi got her PhD in atmospheric dynamics in the Massachusetts Institute of Technology a few years ago. After that, she moved to the University of Hawaii for a couple of years. And then now she's a senior research scientist in NOAA, University of Colorado in Boulder. She has a really long list of scientific services to national and international communities, very impressive career. I just want to mention a few of those that are more relating to the Arctic research, so they're going somehow relating to the topic of today. For example, Hemi is a co-chair of the task team of sea ice prediction and verification in the YOP Polar Prediction Project. She leads the research of the Clover Creek Northern Ocean regions, and it's a pleasure for me to join in with this group. She's also a member of the High Latitude Processes Working Group at the Atmospheric System Research of the DOA, US DOA. And to get closer to the topic of the day today, Amy is going to present. I want to mention that she's the international leader to organize the forecast guidance in support of the MOSAiC campaign. So MOSAiC stands for multidisciplinary drifting observation of the study of the Arctic climates, and represents the largest expedition in history into the central part of the Arctic region. So we got during one long year expedition with camp and using the polar stern, very large, enormous amounts of data. Amy is using some of those, and that's what she's going to present today. Amy today in details will work on the improvement achieved in the short-term forecasting of the Arctic ocean sea ice atmosphere cable system using results of the MOSAiC campaign. Before leaving the floor to the talk, I just asked Amy to wait a few minutes to let me present a few slides on CMCC. So CMCC, the Euro-Mediterranean Center on Climate Change, is a no-profit organization that was established in 2005 to become in 10 years a foundation, so in 2015. The CMCC scientific research focus on the really wide range of aspects of climate change, and mainly the interaction of these changes with the environment, the societies, the making of business and political decisions. The center has really articulated structure. There are many institutions involved in that. They are all organized in a well-connected network that goes through the entire peninsula, including Sardinia. There are many institutions. There are private institutions or also universities. And all our research activities are shared among quite a large number of research divisions, as you see here on the schemes on the slides. And it's clear from this list that actually the knowledge skill that we have as CMCC cover a lot of topics all relating to climate change, from the poor numerical modeling and this application to the computer science, data management, to the analysis of climate impact, the assessment of the risk, and then to conclude the sharing of outcome with the external communities. So the main outcomes, the main achievement that we have in our research activity at CMCC are shared with the classical, in the classical way with the scientific community through papers, scientific publication, with talks at international and national conferences. But we also are involved a lot in educational programs, and in public event and communication activities for more generic public. And of course, for the communication, I want to mention that the webinar and the internal seminar at CMCC cover a really large part of our dissemination, as the webinar that today we are going to have. And that brings me back to Amy. So for asking questions during your talk, you have two different ways. One is to raise the hand as Zoom allowed you to do, or you can write into the QA section based on the bottom of your screen. And everything will be recorded and available in a few days online into all the social CMCC channel, probably also through the CMCC website. So if you miss something or whatever happens to your connection, the Amy's talk will be anyway available. And then, so Amy, I'm going to shut down my voice and close my my webcam. You can take the floor. And thanks for being here. Thanks for sharing your recent studies. And again, Amy today is going to present the new achievements and new results on short-term forecasting of sea ice, atmosphere, and ocean into the Arctic region. So go ahead, Amy. Thanks a lot.
So thank you, Dorotea. It's really a pleasure to open this series of webinars. Here, I'll share my screen. Can you see that okay?
Yes, we can.
Okay, thank you. So the title is changed a little bit from what Dorotea was showing, just because I'm now looking at not just the MOSAiC observations, but the Sheba campaign as well, which was also a year-long drift experiment that took place about 22 years ago. So I'll be talking, I was really interested in comparing these two campaigns and using both of them to evaluate our short-term forecasts during MOSAiC. And it's really been my pleasure to work in this lab, the Physical Sciences Laboratory here in Boulder, Colorado. I'm working with a number of people that were instrumental in both of these campaigns. So it's really a pleasure to be a part of this team. And the motivation for this work, this is showing the skill of forecasting of sea ice volume from 0 to 60 days. And it's the skill score here, if the lower number means higher skill. And so if you look at this thin black line, it shows the skill of a persistence forecast. This horizontal black line is the skill of a climatological forecast. And all of the colors are forecasts from different state-of-the-art forecast systems. And the first thing to note is that all of the models have less skill than persistence for up to a 2-day forecast. And that's because there is such limited observations to initialize these forecast systems. But what's of interest to this study that I'll be presenting today is that only one of these models has better skill than climatology after about 14 days. And so what this highlights is this yellow line is the most recent version of the ECMWF model. And what it shows is that if we can improve our physical parameterizations, we can increase the skill of the forecast out to about 40 days. So this figure is showing the observed bimodal distribution of the net surface long-wave fluxes. What these figures are showing on the y-axis is the surface net long-wave flux, so downwelling minus upwelling long-wave fluxes, as a function of the low-level stability, which is the near-surface air temperature minus the skin temperature. And the left figure is from the ARM site, the Department of Energy ARM site at Barrow, Alaska, and the right is from the Sheba campaign. And what you see in both of these is this bimodal distribution. So in observations, we have a clear sky mode with a very large outgoing long wave radiation and very large low level stability because the surface is cooling so much faster than the atmosphere. But we also have a cloudy mode, which has very small surface net long wave radiation because the cloud driven downward long wave radiation almost cancels the outgoing long wave radiation. And we also have very small low level stability because the cloud driven mixing causes the near surface environment to be very well mixed. This is showing the same diagnostic, but from 11 CMIP5 models. So this is just for wintertime, November to February. And what you can see generally is that these models only are unimodal. They only have one mode. They only have a clear sky mode. Very few have a cloudy mode. And that's because even now, models are really challenged to maintain liquid in clouds at very cold temperatures. And also, if you look at these, for example, the third row, these are all these unimodal, so just a clear sky mode. You can see large variability in the clear sky mode as well. For example, in the upper row, the third column, you can see that this model, the MRI model, has the surface net long wave radiation for the clear sky mode is very close to what observations show should be for the cloudy mode. And if you look at the model below it, the IPSL model, it has the low level stability for the clear sky mode is very close to what observations show for the cloudy mode. And so this is just to show that this bimodal distribution, the models are challenged to simulate both the clear sky mode and the cloudy mode. And one of the main challenges for maintaining this cloudy mode is that the prevalence of mixed phase clouds in the Arctic, that's when clouds have both cloud liquid and cloud ice simultaneously. And on the right here, this is from the Morrison et al. 2011 review paper, which highlights some of the very important feedback loops in the maintenance of liquid in these mixed phase clouds. And so I'll just talk about 3 of these feedback loops. Like if you look at this red feedback loop, it shows if, for example, you have a random updraft in the a production of supercooled water, because of the downward long wave radiation that causes surface radiative heating, which increases the availability of moisture and energy for the maintenance of the supercooled water. So that's a positive feedback loop. And this yellow feedback loop, so again, we start with the supercooled water, which causes this cloud top radiative cooling, which drives cloud-driven turbulence, which again maintains the supercooled water. And then there's this third feedback loop, this blue one. So again, we start with the supercooled water, which if we have aerosols that can form ice, we have ice formation. And because of the Bergeron process, water vapor is depleted on cloud ice rather than cloud liquid, which depletes the amount of water vapor available for supercooled water, and the cloud can dissipate. And that's the main feedback loop. It's a negative feedback loop that models cannot simulate. The other challenge is simulating stable boundary layers in the Arctic. This on the right here, this is a study from Sternstrom et al. 2005, which used observations from the Sheba campaign to evaluate many of these processes in these regional climate models. And so what this figure shows, this is the scale sensible heat flux. On the y-axis, that's sensible heat flux divided by wind speed, relative again to the low level stability. And the gray dots show the observations from the Sheba campaign. And the thinner black dots are from 4 of the state-of-the-art regional climate models. And so if you look at the gray dots first, you can see for negative stratification, so that means the surface is warmer than the atmosphere, you're getting positive sensible heat fluxes, so fluxes from the surface into the atmosphere. And then as you get this transition towards positive stability, so stably stratified boundary layers, you see that the sensible heat fluxes go to 0. And that's because when the atmosphere becomes so stably stratified, it shuts off the turbulence. And as you can see, only one of these models even begins to simulate this variability. And most of these models, 3 out of the 4, have these straight lines here, which means they use constant transfer coefficients in their parameterizations for their sensible heat fluxes. And what that means is that as the model becomes more and more stable, the fluxes get larger and larger. And one of the hypotheses is that's what's preventing the models from producing stably stratified boundary layers. And this paper was done in 2005, but this is still an issue in models today. So I'm going to talk about these 2 campaigns, these 2 year-long campaigns. As far as I know, these are the only year-long campaigns in the Central Arctic, except for the Fram expedition, which happened in 1893, led by Nansen. And so the MOSAiC campaign, which ended last year, was from fall of 2019 to the fall of 2020. And the Sheba campaign was from the fall of 1997 to the fall of 1998. And you can see the MOSAiC campaign took place in the Atlantic Arctic, while the Sheba campaign took place in the Pacific Arctic. So there are 2 unique aspects of these 2 campaigns that I want to highlight. The first is that they take place over a full annual cycle. And these 2 figures are from the Pithet and Rotson 2014 paper. And if you look on the left here, showing the seasonal warming, what this figure shows are all the processes that contribute to winter warming on the y-axis and summer warming on the x-axis. So I just want to talk about this one point here, the ocean point. So ocean feedbacks contribute to a cooling in the summer, so heat goes into the ocean in the summer. And then there's a warming in the winter, so the heat goes out of the ocean in the winter time. And so this just shows the seasonal redistribution of energy, which is so critically important in the Arctic. And this is really important because the largest Arctic amplification is happening in wintertime, and it's driven primarily by the processes happening in summertime. And the second unique aspect are these consistent measurements of the fully coupled system. And that's what's highlighted on the right here. So this figure on the y-axis shows how each of these processes is contributing to Arctic warming. And on the x-axis, how each of these processes is contributing to tropical warming. So if the process is contributing more to Arctic warming than tropical warming, it's contributing to Arctic amplification, and the process will be above this gray diagonal line. And so what's really important here is that you can see there are many processes contributing to Arctic amplification, and it's their relative magnitude that determines the net Arctic amplification. And what these studies have shown is that all the different climate models simulate each of these processes differently. And so what we need from observations is the ability to constrain the relative magnitude of these different processes. So why am I looking at both of these campaigns? Well, it's really interesting to look at how the coupled system differs in the Pacific Arctic relative to the Atlantic Arctic. For example, in the Atlantic Arctic, in the wintertime, which is what I'm focusing on here, there's more impact from lower latitudes. There's more advection of heat and moisture from lower latitudes through the Fram Strait, as there is in the Pacific Arctic. Also, it's very interesting to look at how the coupled system responds to different sea ice environments. MOSAiC had much thinner sea ice than the Sheba campaign. And so we can start to look at the different processes and how they interact over different sea ice conditions. And also, it's been 22 years since Sheba. And that was one of the motivations for MOSAiC. Can we identify if the Arctic climate system is changing? And are there emerging feedbacks that we can identify by comparing these 2 campaigns? And specifically what's interesting to the study that I'm presenting here is that putting the variability together from both campaigns, we can get more robust statistics of the coupled system and get a better understanding of the process relationships in the Arctic, which may not be as important for evaluating a forecast system, but it will be when we evaluate the climate models. And so we're using these observations to determine first whether the forecast systems are simulating the observed coupled system, and also if there are biases, can we identify the physical processes responsible for those biases? So this figure is showing the wintertime net long-wave surface fluxes. And wintertime here is defined as October 15th to March 15th, which is the period without any solar radiation. And so in these figures here, I'm showing black and blue as the MOSAiC campaign. And I'm using observations from 4 different sites during MOSAiC. So just as a sanity check, I'm plotting the average over the sites as well as the sum over the sites. And the red in these figures is from the Sheba campaign. And so using liquid water path from these campaigns, I identified clear sky period and the cloudy period. So for net long wave surface fluxes less than minus 25 watts per meter squared, I'm calling clear sky. And I'm calling cloudy sky, actually it's anything greater than minus 25 watts per meter squared. But I'm also defining a third mode here, which are thin clouds, which I'll talk about in a minute. So I'm calling cloudy sky net long wave fluxes greater than minus 15 watts per meter squared. And so what you see here in this figure on the left is that the Sheba campaign was much more bimodal. So there are very few of these thin clouds during Sheba, while as in MOSAiC, there are quite a number of cases. So this figure here, this is the relative frequency. So these are the PDFs over the whole winter time using hourly average observations. And on the right, what's really interesting is if you look at the cumulative frequency of over the whole wintertime season for minus 25 watts per meter squared, you can see that they're almost the same. So we're getting the same frequency of occurrence of clear sky and cloudy sky for Sheba and MOSAiC, but for the MOSAiC campaign, we're getting more occurrences of these thin clouds. So this is showing on the left these PDFs for skin temperature, and on the right, the air minus skin or the near surface stratification. And so on the left, you can see that in the red, the Sheba campaign is the surface temperatures were much colder. I mean, that's very interesting because actually these are small values here, but over the winter time, there was a colder occurrences in MOSAiC where we had minus 48.3 was the minimum temperature, whereas in Sheba it was minus 43.8. So that's interesting. But there were much colder temperatures during Sheba as compared to MOSAiC. And one thing to note in these different figures is that because of this very bimodal distribution during Sheba, all of the variables I'll be showing also show these bimodal distributions as well. For example, during Sheba, you're getting temperatures during clear sky with a peak of about minus 38 degrees, whereas for the cloudy mode, it's about minus 22, whereas we don't see that bimodal distribution at all during MOSAiC. And that's really interesting, and that's why it's really important to look at more than one campaign, because when we only had Sheba, when we only had observations from this one campaign, we assumed that these distributions should all be so bimodal. But what MOSAiC is showing is that that was really just specific to that Sheba year. So that was interesting. And on the right here, so the near surface stratification, you can see that for Sheba, there is this shift towards more positive values. So you're getting many more occurrences of very stably stratified boundary layers during Sheba as compared to MOSAiC. So this figure is showing the ice surface temperature. So over the whole winter time in both campaigns, there was a snow layer. So what this is showing is the temperature at that interface between the snow and the ice. And what this is showing is that even though I just showed the Sheba temperatures were much colder than MOSAiC, their ice temperatures are much warmer. And the ice was thicker during Sheba as compared to MOSAiC, and we know that sea ice grows faster for thinner ice as opposed to thicker ice. But this is showing that the surface of this ice is much warmer for Sheba as compared to MOSAiC, which was not expected at all. And so that is another process which can cause the sea ice to grow faster for the thinner ice, in addition to what we already knew about the growth of sea ice. And so during MOSAiC, the ice thickness was about 0.4 of what was observed during Sheba at the very beginning of winter. And at the end of winter, it was about 0.7 times what the thickness of the sea ice during Sheba. So the MOSAiC sea ice increased by 0.9 meters over the winter season, while in Sheba it only increased by about 0.6 meters. And this is one of the reasons why. So we started looking into what caused the temperatures of the top of the ice to be so warm during Sheba as compared to MOSAiC. And so this is showing the conductive ground flux. And so that's the flux into the ice from the surface. And again, you can see this very bimodal distribution during Sheba, which is not observed at all during MOSAiC. And you can see here, so what this is showing is that you're getting about 0 conductive ground fluxes for the cloudy mode during Sheba, and about 30 watts per meter squared flux out of the surface for the clear sky mode, which is similar to what MOSAiC has. But you can see that this cloudy mode that was observed during Sheba is absent during MOSAiC. And you can also see that MOSAiC has this shift towards more positive values as compared to the Sheba campaign. So we really wanted to try to figure out what's a coupled perspective that can help us really understand this variability. And so we're looking at this from a surface energy balance perspective. So assuming an infinitesimally thin surface layer, the surface energy balance is that the ground flux plus the net radiation plus the sensible heat flux plus the latent heat flux have to balance. And in the Arctic, it's even simpler in the wintertime in the Arctic. The ground flux, and I'm using here, this is a little confusing, but the sign definitions generally used, which is the ground flux and the sensible heat fluxes are positive upward, and the long wave net is negative upward. So I apologize for that, but just to continue to keep the generally used definitions. But the balance is much simpler. So the ground flux minus the net long wave flux plus the sensible heat flux balances. And so to try to look at that from a diagnostic perspective, and to look at how the cloudy modes and the clear sky modes and the thin cloud modes differ between these two campaigns. What I'm plotting here on the y-axis is the sensible heat flux. On the x-axis is the conductive ground flux. And the different colors are the different modes. So black for the cloudy mode, green for the thin cloud mode, and blue for the clear sky mode. And Sheba on the left, MOSAiC in the middle, and then adding the two together on the right. And so what you can see is during Sheba, we're getting much larger or downward sensible heat fluxes during the clear sky mode as opposed to MOSAiC. Whereas during MOSAiC, the cloudy modes have much larger positive ground fluxes as compared to Sheba. And what's interesting is when you put them together, you get a better understanding of the process relationships between these three components, which have to balance between the sensible heat flux, the net long wave fluxes, and the conductive ground fluxes. And so it's really interesting to look at the net impact of these fluxes by integrating them over the course of the winter. And so here I'm showing Sheba on the left and MOSAiC on the right. So the sensible heat fluxes are in black. The ground fluxes are in blue, and the net long wave fluxes are in red. And so you can see, because of these different processes, because of the thin clouds that were observed during MOSAiC and the colder temperatures during Sheba, the net impact is a very different balance between these three terms, which during Sheba, the sensible heat flux have a very significant contribution, whereas in MOSAiC, they essentially balance to zero. And the ground fluxes and the net long wave fluxes balance. So we're using these process relationships to evaluate these short-term forecasts of the Arctic system observed during MOSAiC. And we're focusing on these processes that are unique to the Arctic, such as the persistence and maintenance of mixed phase clouds, the representation of the stable boundary layer, atmosphere-snow interactions, and ocean sea ice atmosphere coupling. And we're focusing on short-term forecasts because our hypothesis is that the errors in the representation of fast processes, such as cloud feedbacks and surface fluxes, can cause biases in climate model projections of Arctic climate change. And currently in this forecast evaluation, we have 8 different centers contributing forecasts. We have a few more that are coming online soon. So we have forecasts from our in-house NOAA Coupled Arctic Forecast System, or CAFS, the ECMWF IFS model, the Medio Franz Arpège Gelato model, the Met Norway our own model, the Navy's Navy ESPC model, and then DWD is running these ICON simulations, and then AVI is downscaling them to look at these more high resolution variability. And then we also have the Russian Hydromet model, the SLAV model, and we're also including the ERA5 fields in our evaluation. So this is showing the joint PDFs of near surface stratification. So air temperature minus skin temperature on the x-axis relative to the net long wave fluxes on the y-axis. And this is just using MOSAiC observations in this figure. And so observations are on the upper left compared to 5 of the forecast systems in our evaluation. And so in the observations, again, you can see this bimodal distribution, the cloudy mode and the clear sky mode. And you can see that only one of these models is able to simulate that distribution. Some of these models still have a little bit of water. The IFS has, you can see in this cloudy mode, there's a frequency of occurrence. There's a mode of here that's smaller than observations, but there's still indications of liquid, and there are clouds. And then the Arpège model also has liquid and clouds, but you can see it's not bimodal at all. There's equal frequency of occurrence from the cloudy mode all the way to the clear sky mode. The DWD model has no liquid in their clouds, and the SLAV model has some kind of combination between the clear sky and cloudy modes. And this is that diagnostic again for the surface energy balance. So sensible heat fluxes on the left and conductive ground fluxes on the bottom, and divided into the cloudy mode in black, the thin cloud mode in green, and the clear sky mode in blue. And observations are on the upper left, and then the 5 different forecast systems. And so with this diagnostic, we can start to really drill down on what is causing the biases that we're observing in, for example, the maintenance of liquid water. And so you can see the CAFS model has this very interesting bias, which we're looking into, where for the cloudy mode, we're getting much more frequency of occurrence for negative ground fluxes, which is not, there are a few cases and observations, but that is an interesting bias that we're trying to understand. The SLAV model has some unrealistic thresholds for sensible heat fluxes. The IFS model has some very interesting biases, which I think the DWD model shares as well, where for the clear sky mode, we're getting much larger positive ground fluxes. And that's something that we're looking into, is their representation of snow. So the IFS model has no snow layer. So the skin temperature is the top of the ice. And the DWD model has an implicit snow layer in their sea ice parameterization. So we're looking into whether some of these biases are due to the representation of snow. And the Arpège model, as I showed, has too many thin clouds. And so we're trying to come up with these couple diagnostics to really identify what is causing the biases in these forecast systems. So I showed that the MOSAiC campaign, together with the Shiba campaign, and hopefully other campaigns, we can include that as well, will provide new insights into coupled processes in the Arctic climate system by providing a consistent measurements of the ocean sea ice atmosphere system over a full annual cycle. And the short-term forecasts of these coupled systems are useful for identifying biases in fast processes such as surface fluxes and cloud formation. And this is what determines the evolution of the coupled system. And as I showed, even now, state-of-the-art forecast systems still struggle to maintain liquid in clouds at cold temperatures. And and the focus that we're looking at is the energy transfer between the different components of the coupled system. And in order to understand that, we have to have a more holistic approach that takes into account the interaction of these different components of the climate system. So thank you for listening, and I really look forward to your questions.
Thank you, Jaime. Thanks a lot for the really nice talk. There are no questions now into the chat, and there are no hands up for that. So that means that actually I can start with my question. I have a couple for you. First of all, is probably really general question that I bet can open the discussion also with other participants. Is you mentioned actually all the focus of your talk is in showing how observation can help to understand the caveat into the models numerical system. And as you say, we should use observation to constrain actually the numerical system models. That means that, I mean, sometimes we really miss the physics that are behind the processes. So it's really hard if you don't know the process to improve or to parameterize things into the numerical system. So you think that actually having different methods like all the data simulation method, or even artificial intelligence using data from this kind of campaign could be a way actually to improve the numerical system. So not improving the system itself, but improving the way that we constrain the model using observation. That could be a kind of more efficient way probably to go.
Definitely. I mean, in terms of a lot of the parameterizations used and the coefficients used in these parameterizations, I definitely think that using some of these higher order statistical techniques will help us to constrain those and determine whether the form of the parameterizations is correct. I mean, in so many of these cases, we're assuming linear relationships, and as I showed, that's clearly not true. Yeah. And so, yes, I agree. And there's so much data that's been taken in these campaigns, and I'm really looking forward to seeing how these different statistical methods can be used to pull out those relationships. Yes.
And to be more specific, you mentioned the snow and the difference that you show between the two campaigns for the growing of sea ice thickness. You mentioned that actually can be due to the difference into the snow cover, and also the difference that you have into the sea ice temperature. And if you look at this, at least the climate simulation, like CM5 or CMCC exercises, the snow component is still really, really weak. And actually it's the same in sense that it's poorly represented somehow. And also probably, I'm not really sure into the models that you're presenting here for the forecast systems, but it's never really the main component that we look at or we focus on when we work into the coupled systems. So you think that actually snow can be one, probably not the driver for this kind of study, but anyway, main component that we should start to focus on?
Oh, definitely, definitely. No, the representation of snow in terms of the growth of the sea ice is critically important. Because if you look at the parameterizations for conductive ground fluxes, in that equation, it's divided by the snow depth. So if you have 10 centimeters of snow or 20 centimeters of snow, which is almost within our observational uncertainty because of things like blowing snow and other things, it can change the conductive ground fluxes by a factor of 2.
Okay.
So, so it's critically important. And one thing that we're really working on is trying to understand what the observations are saying about snow properties. And it's even now very difficult to understand the thermal conductivity of the snow based on just the different crystal properties. And we're still struggling with how to adequately characterize these properties. And so hopefully that's something that will come out of MOSAiC so that we can have the observations we need to develop these better parameterizations of snow. And it's because in the model that I'm using, the CAPS model, we have a snow layer, but it's one layer. And and people have shown that's not sufficient. You need to have at least 3. And so luckily the Arome model, the Met Norway model, has a 12-layer snow model. And so that's what's so interesting about these different forecast systems is we have a whole range of different representations of the climate system. We have some without snow, we have some implicitly have snow, we have some with 1 snow layer, some with 12 snow layers, and we can really try to get at how these different representations affect the representation of the coupled system.
I'm happy to say that into the new CIS model that we're using at CMCC, we have 3 layers for snow.
Oh, that's perfect.
And not that bad. But I think what's also missing for snow is the fact that we are increasing a lot the physics into the CIS components, like the different categories and types, but we are not doing the same with the snow component. That is changing as fast as CIS anyway.
So you have a couple forecast system?
Yeah, we have forecast system for seasonal actually forecasting.
Oh, seasonal, okay.
Yeah, and I'm not really into that, so probably they're going to shorter time scales. But people working on that are into the audience, so probably we will have comments. There are questions coming. So one is from Silvio Gualdi, that's actually leading the group that is working on forecasting. And he's asking, I mean, I'm just reading for the first time with you. We have applied these analyses to short-term forecasts. Do you think it's also applicable to long-term prediction, such as seasonal forecasts? That's what we have. Or are there reasons you don't think these diagnostics are appropriate for those systems? So what you show here on the short-term forecasting can actually be moved to the seasonal one?
Definitely, and that's what we're moving towards. And that's why I show the surface energy balance diagnostic is we're trying to move towards more general process relationships that can be applied to seasonal and longer forecasts.
Good.
So that's one of the main efforts of our team right now.
Oh,
so
great.
not just, you know, initialized short term, but these forecast systems that, I mean, after a season, you don't know what's causing what. You know, is it because of the liquid in the clouds or the impact on the surface? So that's why we're focusing initially on the shorter term forecasts, but we hope to use what we're learning to evaluate the longer forecasts as well.
Good. The second question comes from Elena Bianco, the PhD students at CMCC in drawing program of University of Bologna. She's asking if how important is the ice thickness in the quantification of snow, sea ice, and atmosphere processes. So how sea ice thickness is probably driving the interplay among the different components. And should we be looking at differences between first year ice and multi-year ice, thicker ice?
Definitely, definitely. And that's really interesting because I mentioned that we're using 4 different sites in the MOSAiC campaign, and they actually chose those sites because of their different types of sea ice. And so I don't have that information from the Sheba campaign, and that's why I presented more of an averaged perspective, but we can look at that with the MOSAiC campaign. The ice changes by a factor of 2 between the different sites. Yeah. And so we can start looking at these different categories of ice. But one thing I just wanted to point out is that, yes, I agree, that's really important. That's something we will be looking at, but these processes at the air snow interface are much larger, and the variability is occurring on a much more rapid time scale. And so I believe, my understanding is that it's more important in terms of this growth of the sea ice, and showing that the sea ice during MOSAiC is 6 degrees colder than Sheba. So that's much larger impact, I think, on the growth of the sea ice than the other processes, such as the ocean temperatures, which aren't changing at all. But so that's something we need to quantify, but that's sort of our working hypothesis.
Okay, and staying on the same kind of question, you think that will still make sense to divide between first year and multi-year ice into the Arctic, or we should start, as we do for the Southern Ocean, to look at the characteristic of sea ice. So marginal ice, pancakes, or compact ice, that probably will help more, or will allow us to go more easily into the processes.
I agree. I mean, because it really isn't very, I mean, there's minimum amount of multi-year ice now.
Yeah.
And they're finding really interesting things in MOSAiC. The different types of ice and the different, like the dirty ice and the ices, there's so many different types of first year ice that, yes, I agree that it's the properties that matter. Because these other categories, the thicker ice, the multi-year ice, they're disappearing.
Yeah.
So it's not as useful a characterization as it used to be. Okay,
and just a curiosity, that is not really relating to your talk, sorry for that, but you know if there are actually data sets coming out of MOSAiC from the wave into the Arctic?
Waves into the Arctic?
Yeah, ocean waves. So.
I'm not sure. I mean, I don't know if you check the Pangea site where all the data sets are being archived. The data sets are being archived there, like every day there's new data sets.
Yeah, sure. I think I will check, because it's really nice how actually waves and the new structure of sea ice are starting to interact into the Arctic too. So another way actually to avoid the first year multi-year ice or the marginalized epoch ice is actually to categorize sea ice based on interaction with waves. But that's I mean, into the observational data set is really missing, and even from the numerical point of view, the data set is not really wide, mainly at high latitude. So it's really uncommon, yet uncommon to do that. So that would be a nice improvement.
That's a really interesting perspective. I mean,
well,
I know
we can talk about that in other occasions.
Yeah.
So I don't know if there are other questions. So if someone can also actually ask orally his question or make comments. We have still some minutes left. So if you have other comments or questions for Hemi, you're really welcome. Okay, so nothing is coming. So I really want to thank you, Hemi. Thanks a lot for this discussion. And I've been really pleased to open this series of seminar on the Arctic with you. So thanks a lot. Thanks for this overview on your study on the atmospheric part using MOSAiC. Many thanks. Hope to see advances in that pretty soon.
Thank you very much.
Thanks a lot. It's been a pleasure to have you here. So thanks to all the participants. I'm going to share again the screen for a second, because I just want to invite you, Hemi, and then all the others to the next seminar of this series. Is going to be moderated by Simona Massina, that is the leader of my division. The speakers will be Marika Holland from NCAR. And we were going to have the seminar next week on 15th of September, 4 p.m. Italian time. I mean, you're really welcome to circulate this seminar around, and of course to join in if you have time. So thanks a lot to everyone. Thank you, Hemi. I hope to see you soon in person.
Thank you.
And enjoy your day. I think it's morning in Boulder, right?
Yes.
Yeah, so we are going to close our day. So enjoy your working day.
Thank you, everyone.
Bye-bye, everyone. Thank you, Amy.